Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something to ponder that might just pleasantly overwhelm your mind. When we look out into the cosmos, we instinctively imagine a boundary, a place where the universe simply stops. Perhaps a cosmic wall, or an infinite void beyond. Our brains are wired to think in terms of containers and limits. If you travel far enough in any direction, surely you must reach an end, right? But here's where the universe politely, yet profoundly, disagrees with our intuition. The very idea of an edge to the universe, in the way we usually conceive it, becomes almost meaningless when confronted with the reality of cosmic expansion and the strange geometries of space-time. Imagine an ant walking on the surface of a perfectly spherical balloon. The ant can walk in any direction, endlessly, without ever hitting a wall or falling off. From its 2D perspective, the surface is infinite, yet the balloon itself has a finite size. Now try to imagine that, but in 3 dimensions for the entire universe. It's a thought experiment that stretches the very fabric of our understanding, forcing us to confront a reality far stranger and more beautiful than any simple boundary could ever be. This isn't just abstract philosophy, it's the cutting edge of cosmology, built on decades of meticulous observation and profound theoretical breakthroughs. It's a question that takes us from the smallest particles to the largest structures, revealing how our universe is put together at the most unexpected ways. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with the most immediate, tangible edge we can observe, the boundary of our cosmic vision. You might think of it as the furthest point you could ever hope to see in the universe. But here's the crucial distinction, and where our intuition starts to break down. This isn't a physical wall or a cosmic cliff that you could somehow fly past. Instead, it's a horizon, much like the horizon you see at sea, but far more profound. This boundary is defined not by space itself, but by time and the fundamental speed limit of the cosmos, the speed of light. It's the region of space from which light has had enough time to reach us since the beginning of the universe. To understand this, quote 2, we first need to grasp a few fundamental concepts. Everyone knows that light travels incredibly fast, about 290 × 458 meters per second in a vacuum. It's the ultimate speed limit in our universe, a constant that all observers, regardless of their own motion, will measure identically. This isn't just a fast speed, it's a finite speed. And because light takes time to travel, when we look out into the cosmos, we are literally looking back in time. Consider the light from the sun. It takes approximately 8 minutes and 20 seconds for sunlight to reach Earth. So when you look at the sun, you're not seeing it as it is right now, but as it was 8 minutes and 20 seconds ago. If the sun were to suddenly vanish, we wouldn't know about it for another 8 minutes and 20 seconds. Extend this idea to stars much further away. The light from Alpha Centauri, our nearest stellar neighbour system, takes about 4.3 years to reach us. So we see Alpha Centauri as it was 4.3 years ago. The Andromeda Galaxy, our galactic neighbour, is about 2.5 million light-years away. When you gaze at Andromeda, You're seeing light that left its stars 2.5 million years ago, long before humans even walked upright. Now, apply this principle to the entire universe. The universe, as far as our current understanding goes, began with the Big Bang approximately 13.8 billion years ago. This means that the absolute maximum distance light could have travelled to reach us since the universe began is 13.8 billion light years. Anything further than that, and its light simply hasn't had enough time to get here yet. This defines a sphere around us, with a radius of 13.8 billion light years, representing the light travel distance to the most ancient observable parts of the universe. This sphere is our observable universe, and its boundary is a cosmic horizon. It's not a physical edge where the universe, quote Fable 4, it's merely the limit of what we can see or interact with because of the finite age of the universe and the finite speed of light. But here's where it gets truly mind-bending, and where the numbers start to swell far beyond that 13.8 billion light years. If the universe is only 13.8 billion years old, and light has travelled for 13.8 billion years, you might logically conclude that the observable universe is a sphere with a radius of 13.8 billion light years. Yet, cosmologists routinely state that the diameter of the observable universe is actually closer to 93 billion light years, meaning a radius of about 46.5 billion light years. How can something that started 13.8 billion years ago be 46.5 billion light years away? This discrepancy is one of the most fascinating consequences of a universe that isn't static, but is actively expanding. The key to understanding this lies in the concept of cosmic expansion itself. It's not that galaxies are moving through space away from us, like cars driving down a road. Instead, space itself is expanding, stretching the distances between galaxies. Imagine you're drawing dots on a deflated balloon. As you inflate the balloon, the dots don't move across the surface. Rather, the surface itself expands, carrying the dots further apart. The same thing is happening with galaxies in our universe. The fabric of space-time is stretching, and this stretching increases the distance between any two widely separated points. So, when light left those most distant galaxies 13.8 billion years ago, the galaxies themselves were much closer to us. But during the 13.08 billion years that the light was travelling across the universe to reach our eyes, the space between those galaxies and us was continuously expanding. The light was travelling through an ever-stretching medium. By the time that ancient light finally arrives here today, the original source galaxy has been carried much, much further away by the expansion of space. This is the difference between the quote 5, how far the light has actually travelled, and the quote 6, how far away that galaxy is now at the moment its light finally reaches us. The light travel distance is 13.8 billion light years, but the proper distance to those most ancient observable galaxies today is about 46.5 billion light years. This means the observable universe, a sphere centered on us, has a diameter of roughly 93 billion light years. This profound concept helps us define the most distant, quote 7 cambi of our vision, the cosmic microwave background, or CMB. The CMB is often called the quote 80th of the universe. It's the oldest light we can detect, originating from a time about 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that electrons were not yet bound to atomic nuclei. Instead, they were free, constantly scattering photons, making the universe opaque like a dense fog. Light couldn't travel far without being absorbed or deflected. But as the universe expanded and cooled, electrons combined with nuclei to form the first stable atoms, mostly hydrogen and helium. This event, known as quote 9 or made the universe transparent. The photons that had been trapped were finally free to stream across the cosmos. These are the photons we detect today as the CMB. They've been travelling for nearly 13.8 billion years, and they represent the outermost visual boundary of our observable universe, the surface of last scattering. It's an edge of information, not an edge of existence. It's crucial to understand that this observable universe is inherently observer-centric. Just as you are at the center of your own visual horizon on Earth, you're at the center of your own observable universe. An alien astronomer in a galaxy 10 billion light-years away would have their own observable universe, centered on them, and it would overlap significantly with ours, but also extend into regions that are currently unobservable to us. This means that the universe beyond our observable portion is not empty, nor is it non-existent. It's simply beyond the reach of light that has had enough time to travel to us since the Big Bang. The observable universe, vast as it is almost certainly just a tiny fraction of the entire universe. We have no direct observational evidence for what lies beyond our cosmic horizon, but there's every reason to believe it continues, possibly extending infinitely. Our perspective is limited by the speed of light and the age of the cosmos, providing us with a window into a truly immense and potentially boundless reality. This leads us naturally to the next profound question. If the observable universe has no true edge, but merely a horizon of information, what about the entire universe? Is the entire universe finite or infinite? And if it's finite, could it still have no edge, similar to our ant on a balloon? That question takes us beyond the limits of what we can see, into the realm of cosmic shape and topology, which we'll explore in our next chapter. So, we've navigated the shimmering veil of the observable universe, understanding that its edge is really a horizon of light and time, not a physical barrier. It's a boundary that shifts with every passing moment, expanding as more light from distant galaxies finally reaches our eyes. But this leads us to an even grander, more profound question, doesn't it? One that stretches the very fabric of our intuition. What about the entire universe? The cosmos beyond our cosmic horizon? Is it truly infinite, stretching forever in every direction? Or is it finite, perhaps even having a strange, unseen edge that defies our everyday understanding? This is where we dive headfirst into the fascinating world of cosmic geometry and topology. When physicists talk about the quote 14 of the universe, they're not imagining a giant cosmic potato floating in some larger void. Instead, they're referring to the curvature of space-time itself, how space bends, warps, and connects. Think of it like this. If you were an ant living on a two-dimensional surface, you could tell if your world was flat like a sheet of paper, curved like the surface of a sphere, or saddle-shaped, simply by performing geometric experiments like drawing triangles. For us, living in a three-dimensional universe, the principles are the same, just a lot harder to visualize. we talk about three main possibilities for the universe's overall curvature. First, the universe could be flat. Imagine an infinitely stretching, perfectly flat sheet of paper. If you draw two parallel lines on it, they will never meet. This is the Euclidean geometry we learned in school. In a flat universe, space is infinite and continues forever. Second, the universe could have positive curvature, like the surface of a giant sphere. If you draw two parallel lines on a sphere, like two lines of longitude starting from the equator, they will eventually converge and cross at the poles. While the surface of a sphere is finite in area, it has no edge. You can travel forever in any direction without ever reaching a boundary. This is the classic ant on a balloon analogy. The ant never falls off, never hits a wall, but its world is undeniably finite. If our universe has positive curvature, it would be finite but boundless. Third, the universe could have negative curvature, often compared to a saddle or a Pringle potato chip. In this geometry, parallel lines would actually diverge, spreading further and further apart. A universe with negative curvature would also be infinite, stretching out forever, much like the flat universe, but with a different kind of spatial distortion. So, how do we figure out which one it is? We can't step outside the universe to get a bird's eye view, right? Instead, we rely on the subtle clues left behind in the cosmic fabric itself, particularly the universe's total energy density. Every bit of matter, every photon of light, every whisper of dark energy contributes to the gravitational pull that shapes space-time. Cosmologists have identified as Sustus, quote, 17. This is the precise average density of matter and energy required for the universe to be perfectly flat. If the universe's actual density is greater than the critical density, gravity wins, by pulling space inward, resulting in a positive curvature, a closed, finite universe. If the universe's actual density is less than the critical density, space expands outward faster than gravity can pull it back, leading to a negative curvature, an open, infinite universe. And if the universe's actual density is exactly equal to the critical density, then space is perfectly balanced, resulting in a flat, infinite universe. For decades, measuring this critical density and by extension the universe's curvature has been one of the holy grails of cosmology. And the most powerful tool in our arsenal? You guessed it, the cosmic microwave background, or CMB. Remember that ancient light from 380,000 years after the Big Bang? It's not just a snapshot of the early universe, it's also a cosmic ruler. The CMB isn't perfectly uniform. It's speckled with tiny temperature fluctuations, hot and cold spots. These spots represent the seeds of future galaxies and galaxy clusters, tiny variations in density in the early universe. Crucially, physicists can predict the actual physical size of these hot and cold spots at the moment the CMB light was emitted. Now, here's the clever part. The apparent size of these spots as we observe them today depends on the curvature of the universe. If the universe has positive curvature, it acts like a giant magnifying glass, making the spots appear larger than they actually are. If the universe has negative curvature, it acts like a diverging lens, making the spots appear smaller. But if the universe is flat, the apparent size of these spots will match their actual physical size. So, What do the incredibly precise measurements from missions like the WMAP and Planck satellites tell us? They tell us that the hot and cold spots in the CMB appear to be exactly the size we would expect if the universe were flat. This is one of the most robust findings in modern cosmology. Our universe, according to our best observations, is remarkably flat. This means the total energy density of the universe, comprising ordinary matter, dark matter, and dark energy, is incredibly close to the critical density. And what does a flat universe imply? It implies an infinite universe. If space is truly flat and extends indefinitely, then it must be infinite. This is a mind-boggling thought, stretching our imaginations to their absolute limit. An infinite universe means that if you travel far enough, you'll eventually encounter every possible arrangement of particles, every permutation of existence, perhaps even infinite copies of yourself living out infinite variations of your life. It's a concept that truly challenges our everyday understanding of scale. But here's a crucial caveat, a twist in the cosmic tale that keeps cosmologists up at night. Just because the universe appears locally flat to us, within our observable horizon, doesn't necessarily mean it's globally flat and infinite. Think of it like this. If you're standing on the surface of the Earth, it looks pretty flat around you, right? You can't see the curvature over a short distance. But we know the Earth is a sphere, a finite, positively curved object. The same principle could apply to the universe. Our observable universe is vast, 93 billion light-years across, but it's still just a patch of the entire cosmos. It's possible that the universe could be finite but have a very complex, multi-connected topology, like a giant cosmic donut, a torus, or something even stranger. In such a universe, space would still appear locally flat, but if you travelled far enough in a straight line, you might eventually loop back to where you started, like a game of Pac-Man. It would be finite, yet still boundless, with no edge to hit. You'd just keep going and eventually return. This distinction between local geometry, what we can observe, and global topology, the overall shape and connectivity, is paramount. Our CMB data strongly suggests local flatness. If the universe is globally flat, then it's infinite. But if it's globally curved, even slightly, or has a complex topology, it could still be finite, even while appearing flat within our observable bubble. The current evidence leans heavily towards flatness, making an infinite universe the most straightforward interpretation. However, the possibility of a finite, multi-connected universe that looks flat is still very much on the table, although current data puts very strong limits on how small such a universe could be. It would have to be absolutely enormous, far larger than our observable universe, for us not to have detected its looping nature. So let's revisit our initial question. Can the universe be infinite and have an edge? Based on what we've explored, the answer is a resounding no. An infinite universe, by definition, has no edge. It stretches on forever. And a finite, boundless universe, like a sphere or a torus, also has no edge in the traditional sense. You never hit a wall, you just keep going. The only edge we experience is our cosmic horizon, an edge of information, not a physical barrier. The universe, in its grand design, defies our intuitive need for boundaries and walls. It pushes us to consider geometries and scales that our brains are not naturally wired to comprehend. Whether it's truly infinite, stretching beyond our wildest imaginings, or a finite, boundless expanse that cleverly folds back on itself, the cosmos offers a profound mystery. For now, the best evidence points to a flat geometry, which most naturally implies an infinite universe. But the hunt for definitive answers continues, driving us to build bigger telescopes, design more sensitive detectors, and refine our cosmic theories. In our next chapter, we'll explore some of the more mind-bending implications of an infinite universe and what happens when we push the boundaries of what can exist within such a boundless expanse. Get ready, because the universe is about to get even stranger. Okay, let's dive back into the fascinating world of scientific wonder, where our intuition often gets a cosmic workout. We've wrestled with the idea of a universe that's boundless, perhaps even infinite, yet we still grapple with that persistent question. Can the universe be infinite and have an edge? It feels like a contradiction, doesn't it? Like trying to draw a circle that goes on forever but somehow stops. Our brains are wired for beginnings and endings, for boundaries and limits. But what if the edge we're searching for isn't a spatial one at all? What if it's an edge in a dimension we often take for granted, one that shapes everything we know and experience? Let's talk about time. Think back to our previous explorations. We established that the observable universe, that magnificent sphere of everything we can possibly see, has an edge, our cosmic horizon. But that's an edge of information, a limit imposed by the finite speed of light and the universe's age. It's not a physical wall, it's a boundary to our perception, unique to each observer. Beyond it lies more universe, just out of our current sight. Now, let's consider a different kind of edge, one that is truly universal, affecting every point in the cosmos. We're talking about the ultimate beginning, the Big Bang. Here's something to ponder. If the universe is infinite now, does that mean it always existed? Does infinity in space imply infinity in time? Our intuition might scream, says Stern, quote 21. But the universe, in its boundless wisdom, often delights in defying our expectations. The Big Bang, as our current cosmological model describes it, was not an explosion in space, but rather an explosion of space itself. This is a crucial distinction, and one that stretches the very fabric of our understanding. Imagine a vast, perfectly flat, infinitely stretching sheet of rubber. Now, imagine this entire infinite sheet beginning to expand at every single point, simultaneously. Every single point on that sheet moves further away from every other point, but there's no central point from which the expansion originates, and there's no outer boundary for it to expand into. The sheet was infinite then, and it remains infinite now, just more stretched out. This analogy helps us grasp how a spatially infinite universe can, in fact, have a beginning. The universe, as we understand it, began approximately 13.8 billion years ago in an incredibly hot, dense state. This moment, often referred to as a singularity, though modern physics suggests it was more likely an incredibly compact, dense state governed by quantum gravity, which we don't yet fully understand, represents a true temporal edge. We can't look. Quote 22. The Big Bang, not because there's a cosmic curtain drawn, but because before didn't exist in our universe. Time, as we know it, along with space and matter, came into being with the Big Bang. It's the ultimate start button for everything. This isn't just an edge to our knowledge, it's a fundamental edge to the existence of space-time itself. So, if you're asking if the universe has an edge, the answer is a resounding, quote 24. But it's an edge in time. It's the moment when the cosmic clock started ticking, when the stage for all of existence was set. This temporal edge is absolute, shared by all observers, regardless of their position in the vast cosmos. Every galaxy, every star, every atom, and indeed, you and I, share this common origin. We are all children of the Big Bang. This concept resolves the apparent paradox. The universe can be spatially infinite, or at least boundless and vastly larger than our observable portion, appearing flat, yet still have a finite age. It has a beginning, a birth date. It doesn't need to have existed for an infinite amount of time to be infinite in its spatial extent at any given moment. Let's take a moment to really let that sink in. We're not talking about a universe that started small and then grew to be infinite. We're talking about a universe that could have been spatially infinite from the very first instant of its existence, and it has been expanding ever since. Every point in that infinite expanse has been moving away from every other point, stretching the fabric of space-time, cooling, and allowing structures to form. This means there's no center to the universe where the Big Bang happened. The Big Bang happened everywhere, simultaneously, throughout the infinite expanse that would become our universe. Each point in space was the center of its own local expansion. It's a mind-bending idea, right? But it's what the evidence, particularly from the uniform nature of the cosmic microwave background radiation, strongly suggests. So, we have identified a very real, fundamental edge to our universe. Its beginning. It's a temporal boundary, a cosmic genesis. But are there other kinds of, quote 28, sir, we might consider? We've already touched upon the edge of observation, our cosmic horizon. This is an information boundary, a limit to what light has had time to reach us. Closely related to this is the edge of causality. Imagine regions of the universe so incredibly distant that even light, travelling at its breakneck speed for 13.8 billion years, hasn't had enough time to bridge the gap between them and us. These regions are beyond our causal horizon. No information, no force, no interaction originating from those regions could have possibly reached us since the Big Bang. They are, in a very real sense, causally disconnected from us, forming and thus, quote 29, to our immediate cosmic influence and interaction. While they are still part of the larger universe, they exist beyond our capacity to ever directly interact with them. Then there are the edges of understanding. These aren't physical boundaries in space-time, but rather frontiers of our knowledge. Consider dark matter and dark energy. Together, they make up about 95% of the universe's mass-energy content, yet we understand very little about them. Dark energy, in particular, is responsible for the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. These mysterious components represent the quote 30 of our current scientific comprehension. They challenge our models, push the limits of our theories, and beckon us to explore deeper into the fundamental laws governing the cosmos. They are not spatial edges, but they are very real conceptual boundaries that define the limits of our present scientific grasp. So, when we ask, quote 31, the answer is a nuanced but definitive, Quote 32. 1. Spatially, the universe appears to be infinite and boundless. Our best data points to a flat geometry, which, if truly global, implies infinite extent. In such a universe, there is no physical sus quote 33 or sus 34 some you could reach, no point where space stops. You could travel forever without hitting an edge. 2. Temporally, the universe has a very clear edge, the Big Bang. This is the beginning of spacetime itself, a shared origin for everything within our cosmos. It's a finite age for an infinite expanse. 3. Observationally, each observer has a cosmic horizon. This is an informational edge, a boundary to what we can see, not to what exists. 4. Causally, there are regions beyond our causal horizon. These are beyond our ability to interact with, representing a practical edge to our influence and connection. 5. Conceptually, our understanding has edges. Dark energy and dark matter are powerful reminders that there are vast territories of knowledge yet to be charted, representing frontiers of scientific discovery. The universe, in its profound elegance, manages to be both endlessly expansive and fundamentally finite in its history. It's a beautiful contradiction, a testament to how the cosmos continually challenges our human-centric notions of what's possible. It doesn't conform to our neat boxes of quote 36. Instead, it embraces the complexity of quote 37. Our journey into the universe's boundaries continues to reveal that the edges we perceive are often reflections of our own limitations, whether those are the limits of light speed, the limits of time itself, or the limits of our current scientific understanding. The universe itself, in its grand, sweeping totality, seems to offer no spatial end. But what if there's an even grander canvas? What if our infinite, boundless universe is just one of many? Could there be an quote 39 to our universe, in the sense that it's just one bubble, one island, in an even larger, more encompassing reality? We're talking about the tantalizing, speculative, and deeply thought-provoking concept of the multiverse. That, my friends, is a whole new dimension of edges and infinities, and it's a topic we'll be eager to explore in our next chapter. All right, so we've journeyed through the vast expanse of our observable universe, pondered its flat geometry, and wrestled with the idea of its potential spatial infinity, or boundless, multi-connected topology. We've grappled with the Big Bang as a definitive temporal edge, a beginning for everything we know, yet one that happened everywhere, not from a singular point in pre-existing space. We've even acknowledged the edges of our current understanding, those tantalizing mysteries like dark matter and dark energy that make up the lion's share of cosmic reality. But what if all of this, the 93 billion light-year diameter of our observable sphere, the potentially infinite cosmic sea beyond, the very fabric of space-time born from the Big Bang, what if this is not the entire story? What if our universe, immense and awe-inspiring as it is merely one among countless others? What if it's just a single bubble in a frothing, infinite cosmic ocean? Welcome, fellow explorer, to the mind-bending, deeply speculative yet scientifically motivated realm of the multiverse. Here, our concept of edges stretches and transforms once again, pushing the very boundaries of what we conceive as existence. The idea of a multiverse isn't just a flight of fancy from science fiction. It arises from several different corners of theoretical physics, each attempting to resolve profound puzzles within our own universe. It's a testament to the scientific method's relentless pursuit of deeper truths, even when those truths challenge our most fundamental intuitions. Let's dive into some of the leading ways scientists envision these other universes and what they might imply for the notion of edges. First, let's revisit something we touched upon in Chapter 2, the idea of an infinite universe that is spatially flat. If our universe truly extends infinitely in all directions, and if matter and energy are distributed in a somewhat uniform way, as cosmology suggests on the larger scales, then every single possible configuration of particles must eventually repeat. Think about it. There are a finite number of ways to arrange particles within a given volume. If you have an infinite volume, then any arrangement, no matter how complex, including one that perfectly replicates you, reading this right now on an Earth identical to ours, must occur an infinite number of times. This is what some call a multiverse. Or, more simply, the infinite extension of our own universe. It's not about separate universes with different laws, but rather an infinite number of identical or near-identical regions within our universe, simply too far away for us ever to observe or interact with. In this scenario, the edge of our universe remains elusive because there is no external edge. It just keeps going, forever, repeating patterns. It's a universe that contains an infinite number of observational spheres, each centered on its own observer, each one's observable universe, indistinguishable from the next. The edge here is still our cosmic horizon, an informational limit, not a physical barrier to the universe itself. Now, let's turn up the dial on the strangeness. Imagine the universe didn't just expand, but experienced a period of unbelievably rapid exponential growth in its earliest moments, a phenomenon called cosmic inflation. This theory elegantly explains several features of our universe, like its remarkable flatness and the uniformity of the cosmic microwave background. But here's where it gets interesting. If inflation happened once, why stop? Many models of inflation suggest that it might be eternal. In eternal inflation, inflation doesn't just stop everywhere simultaneously. Instead, it might continue indefinitely in most regions of a vast overarching meta-space, while occasionally in localized patches it does stop. These patches then bubble off, giving rise to new universes. Each bubble is a Big Bang event in its own right, expanding and evolving, forming its own galaxies, stars, and planets. Our universe, in this view, is just one such bubble. This is the Level 2 multiverse, often visualized as a bubble multiverse, or pocket universes. Picture an endless, frothing sea of cosmic foam, where each bubble is a distinct universe. And here, the concept of an edge takes on a whole new meaning. The edge of our universe would be the boundary of our bubble, a conceptual membrane separating our spacetime from the other bubbles, or from the inflating metaspace itself. Could these bubbles have different fundamental physical constants? Could they have different numbers of dimensions? Absolutely. The random quantum fluctuations that drive inflation could lead to wildly different outcomes in different bubbles. Some might be sterile, collapsing quickly or expanding too fast for matter to coalesce. Others might be teeming with life, perhaps even life forms we can barely imagine. What does this mean for us? We'd be forever confined within our own bubble. No light, no information, no physical travel could ever cross the quote 51 into another bubble universe. The quote 52, here is not a wall you can touch, but an impenetrable barrier of space-time itself, a fundamental disconnect between distinct cosmic realities. Yet the existence of such quote 53 might explain why our universe's constants are so finely tuned for life. If there are infinite universes, then it's not surprising that at least one of them, ours, happens to have the right conditions. It's a cosmic lottery, and we won. Next, let's dive into the bizarre world of quantum mechanics, where reality itself seems to branch. You've probably heard that in quantum mechanics, particles don't have a definite state until they're observed. Instead, they exist in a superposition of all possible states. When an observation is made, the wave function collapses, and one outcome is realized. But what if it doesn't collapse? The Many Worlds Interpretation, MWI, a level 3 multiverse theory, suggests that every possible outcome of a quantum measurement actually occurs, but in different parallel universes. When you make a decision, or when a quantum event occurs, like a photon hitting an electron, the universe doesn't choose one path. It splits into multiple universes, one for each possible outcome. In one universe, you chose coffee. In another, you chose tea. In one universe, Schrödinger's cat is alive. In another, it's dead. Here, the edges are less about spatial separation and more about branching timelines, or divergent realities. You, the consciousness, only experience one branch, one slice of this ever-splitting reality. The edge is the point of divergence, an invisible, uncrossable chasm between parallel versions of existence that share a common past but have diverged into unique futures. It's an edge of causality, an edge of identity, an edge of experienced reality. These universes aren't physically elsewhere in space. They're coexistent, yet utterly separate dimensions of possibility. Finally, for the truly adventurous, we have the Level 4 multiverse, odd and championed by physicist Max Tegmark. This is the most radical and abstract idea, the mathematical universe hypothesis. It proposes that every mathematically consistent structure corresponds to a real, existing parallel universe. This means that not only do universes with different physical constants exist, but also universes with entirely different fundamental equations, different numbers of dimensions, different forms of logic, or even no physical laws as we understand them at all. If a mathematical structure is conceivable and self-consistent, then it exists as its own universe. In this ultimate multiverse, the quote 60 is simply the boundary of mathematical consistency. Anything that can be described mathematically is a universe. This pushes the concept of reality to its extreme, suggesting that our universe is just one of an infinite number of mathematical structures that exist as realities. It's an edge of pure abstract possibility, where anything that makes logical sense exists. So, where does this leave our search for edges? The multiverse hypothesis doesn't provide a neat physical wall at the end of existence. Instead, it multiplies and redefines the very concept of until quote 61. We have the informational edge of our cosmic horizon, still a limit to our observation within our own bubble. We have the temporal edge of the Big Bang, the beginning of our particular space-time. We have the bubble edges of a level 2 multiverse, conceptual membranes separating distinct universes that are forever isolated from one another. We have the branching edges of a level 3 multiverse, the points of quantum divergence that split reality into parallel timelines. And we have the conceptual edges of a level 4 multiverse, defined by the limits of mathematical consistency itself. It's crucial to remember that these multiverse theories are at present highly speculative. We don't have direct observational evidence for them. How would we test them? It's one of the biggest challenges in modern cosmology. Perhaps subtle gravitational imprints from a collision with another bubble universe could be detected in the cosmic microwave background. Or maybe we'll find anomalies in the distribution of matter that hint at an interaction with a parallel reality. But these are complex and hotly debated ideas. What the multiverse does, however, is profoundly expand our imagination and challenge our anthropocentric view of existence. It suggests that the KE, quote 62 world might be far grander, far more diverse, and far more complex than we can currently comprehend. It takes the idea of infinity, which we've been grappling with in the context of our own universe, and applies it to an even grander scale, where not just space, but realities themselves are potentially infinite in number and variety. Ultimately, the quest for edges in the cosmos leads us to ever more abstract and mind-bending frontiers. From the horizon of our vision to the very fabric of space-time, and now to the possibility of countless other universes, we find that edges are rarely physical walls. Instead, they are limits of information, limits of time, limits of interaction, or limits of our current understanding. They are boundaries that define our reality, but not necessarily the entirety of existence. As we continue to push these boundaries, both with our telescopes and our theories, we gain a deeper appreciation for the incredible ingenuity of the universe, or perhaps the multiverses, and our own humble yet extraordinary place within it. In our next chapter, we'll delve even deeper into the philosophical implications of this cosmic vastness and the limits of human knowledge, exploring how these scientific revelations shape our understanding of meaning, purpose, and our very existence in a potentially infinite and multifaceted cosmos. In our last chapter, we ventured into the mind-bending territories of the multiverse, where, quote 64, could represent anything from the limits of our cosmic horizon to the very boundaries between distinct realities, each with its own set of physical laws. We saw that these aren't physical walls in the traditional sense, but rather conceptual frontiers, limits of information, time, interaction, or even the reach of our current understanding. But what happens when we push the concept of an edge even further, to the very fabric of space-time itself, or to the moments where our most fundamental laws of physics seem to break down? What about the edges where the universe becomes so extreme, so dense, or so energetic that our current theories simply throw up their hands? This is where we plunge into some of the most profound mysteries of cosmology and theoretical physics, exploring edges that challenge not just our intuition, but the very foundations of our scientific knowledge. Imagine, if you will, a point, not a place you can visit, but a mathematical concept, where density becomes infinite, where space-time curvature stretches to infinity, and where the laws of physics as we know them cease to apply. We call such a point a singularity, These are the ultimate edges of physical description, places where our equations fail, screaming at us that we've reached a limit in our understanding. The most famous example, perhaps, is found at the heart of a sub-black hole. You're familiar with the idea of an event horizon, right? That's the, quote, 60 of no return, the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. It's a fascinating one-way membrane. But the event horizon isn't the true edge where physics breaks down. That lies deeper, at the very centre of the black hole, where all the mass has collapsed into an infinitely dense point, the singularity. Here, the concepts of space and time as we understand them warp beyond recognition. It's a true edge of space-time, a place where our current models of gravity, based on Einstein's general relativity, simply can't cope. Yet there's an even more profound singularity we've already touched upon, the Big Bang. We discussed it as a temporal edge, the beginning of space-time itself, but it's also a singularity in the sense that, at that initial moment, the entire observable universe was compressed into an unimaginably hot and dense state. If we rewind the cosmic clock all the way back to Tiamat, general relativity predicts an infinite density and temperature, another singularity. This means the Big Bang isn't just a beginning in time, it's also an edge where our current physics reaches its limit. We can describe the universe after the Big Bang with remarkable accuracy, but what happened at or before that initial singularity remains shrouded in mystery, an ultimate frontier of our knowledge. This brings us to another critical edge, the Planck-epoch. This is a tiny sliver of time, the first 1043 seconds after the Big Bang. It's an incredibly short duration, almost incomprehensible. To give you a sense of scale, a blink of an eye lasts about 10 seconds. We're talking about a time interval that is 42 orders of magnitude smaller. During this epoch, the universe was so incredibly hot and dense that all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single superforce. Why is this an edge? Because at these extreme scales of energy and density, the quantum effects of gravity become dominant. Our two most successful theories in physics, general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of matter and energy at the subatomic level, are currently incompatible. They are like two different languages, each brilliant in its own domain, but unable to speak to each other in this extreme environment. The Planck epoch is the edge where our current physics breaks down because we lack a unified theory of quantum gravity. Imagine trying to build a bridge between two towering cliffs, but you only have tools designed for one side or the other. That's our situation with quantum gravity. Theories like string theory and loop quantum gravity are attempts to build that bridge, to describe what happens at this fundamental. Quote 74. They propose that at these unimaginably small scales, the Planck length about 1035 meters, space-time itself might not be smooth and continuous, but rather granular or made of tiny vibrating strings. If we could understand this, quote 75, we might unlock the secrets of the Big Bang itself, and perhaps even the true nature of singularities. Beyond these conceptual, quote 76, where our theories fail, there are also vast, unexplored, quote 77, within the universe that continue to baffle us, constituting the overwhelming majority of cosmic reality. I'm talking, of course, about dark matter and dark energy. Together, they make up about 95% of the universe's total mass energy content. Yet, we have never directly observed them. They represent a colossal, quote, 78 of our current understanding of the universe's composition and dynamics. Think about it. Everything we see, everything we've studied, stars, galaxies, nebulae, planets, us, makes up only about 5% of the cosmos. The remaining 95% is largely a mystery. This is an, quote, 79 of ignorance, a vast frontier waiting to be explored. Dark matter is inferred through its gravitational effects. We see galaxies rotating much faster than they should, based on the visible matter within them. We observe gravitational lensing, the bending of light around massive objects, on scales that can't be explained by visible matter alone. Large-scale structure formation in the universe also points to the existence of an invisible gravitational scaffold. Dark matter acts as a kind of cosmic glue, holding galaxies and galaxy clusters together. It's an, quote, 80 of composition, a type of matter that doesn't interact with light or other electromagnetic forces, making it invisible to our telescopes. What is it made of? WIMPs, weakly interacting massive particles, axions, something entirely new. We're at the quote, of identifying its true nature. Then there's dark energy, perhaps the most perplexing edge of all. Discovered in the late 1990s, dark energy is responsible for the accelerating expansion of the universe. For decades, scientists expected gravity to slow down cosmic expansion, or at least keep it constant. But observations of distant supernovae revealed that the universe's expansion is actually speeding up. This implies an unknown force, or property of spacetime itself, that is pushing everything apart. Dark energy acts as an quote 83. A repulsive force permeating all of space. It's an edge of fundamental forces, or perhaps an edge to our understanding of the vacuum itself. Is it a cosmological constant, an inherent energy density of empty space? Or is it a dynamic field changing over time? The answers lie beyond our current edge of knowledge. These unseen components are not just gaps in our understanding, they are powerful reminders that our current models of physics are incomplete. They are invitations to develop new theories, build new instruments, and embark on new intellectual journeys. The edges of dark matter and dark energy are not barriers, but catalysts for profound scientific revolutions. Now, let's take a truly speculative leap to an, quote, 88 that challenges the very notion of what space and time are. What if space-time itself isn't fundamental? What if it's not the ultimate bedrock of reality, but rather an emergent phenomenon arising from something deeper? This is a radical idea, but one being actively explored in theoretical physics. Imagine the surface of a pond. It appears smooth and continuous, but we know it's made of countless individual water molecules. In a similar way, some theories propose that space-time, the very stage upon which the cosmic drama unfolds, and where all our edges are defined, might emerge from a more fundamental, non-spatial, non-temporal reality. One fascinating avenue of thought connects space-time emergence to quantum entanglement. Entanglement is that spooky quantum connection where two particles, no matter how far apart, remain linked. Measuring one instantaneously affects the other, Some physicists are exploring ideas where the intricate web of quantum entanglement between fundamental degrees of freedom gives rise to the geometry of spacetime. If this is true, then the edges we've been discussing, the Big Bang singularity, the event horizon of a black hole, even the smooth fabric of space, are not fundamental features but rather manifestations of this deeper quantum reality. If spacetime is emergent, then the question of an Brit, quote, 91 Dom takes on an entirely new dimension. It's no longer just about where space stops or where time begins, but what lies beneath or beyond the emergent phenomenon itself. It's like asking for the quote 92s of wetness in a pond. Wetness emerges from the interaction of water molecules. It's not an independent entity with a sharp boundary. Similarly, if space-time emerges, its edges might be fuzzy, context-dependent, or simply disappear at the most fundamental level. This truly stretches the very fabric of our understanding, doesn't it? It suggests that the, quote 94 of the universe are not just physical or temporal boundaries, but also the limits of our current conceptual frameworks. They are the points where our intuitive grasp of reality, shaped by our everyday experience, must give way to the strange and wonderful truths revealed by science. So, as we reflect on this journey, we find that the question, quote 95 on, isn't a simple yes or no. It's an invitation to redefine what we mean by K's quote 96. These edges are rarely solid walls. Instead, they are horizons of information, like the observable universe, defined by the speed of light and cosmic time. Boundaries of topology. Whether the universe is truly infinite or a vast, boundless, finite loop. Temporal beginnings. The Big Bang, the ultimate start of space-time. Frontiers of causality, regions forever beyond our reach. Conceptual divisions between different universes in the speculative multiverse. Limits of known physics, singularities and the Planck epoch, where our theories break down. Vast unknowns, dark matter and dark energy, urging us to discover new physics. Emergent properties, where space-time itself might arise from a deeper reality. Each, quote 97, we've explored is not a barrier to knowledge, but a signpost pointing towards new discoveries, new questions, and new ways of understanding our place in the cosmos. The universe, in its infinite complexity and mystery, constantly challenges us to expand our minds, to question our assumptions, and to embrace the wonder of the unknown. The quest for these edges is, in essence, the quest for a deeper understanding of reality itself. And that, my friends, is why I'm always curious, and why I hope you are too. Keep wondering, keep questioning, and keep exploring the fascinating world of scientific wonder with us. Until next time, let your mind wander the farthest reaches of what's possible and what might just be. We've journeyed through mind-bending concepts, haven't we? From the observable universe's informational horizon to the Big Bang's temporal genesis, and even the tantalizing possibility that space-time itself isn't fundamental. It's a lot to wrap your mind around, I know. But what if the very fabric of reality, the stuff from which everything else emerges, isn't energy, isn't matter, and isn't even space-time? What if it's information? Here's an idea that truly stretches our conventional understanding, an edge that redefines what we mean by fundamental. the notion that information might be the most basic building block of our universe. Imagine a reality where the physical world, the stars, the galaxies, even you and I, isn't just described by information, but is information in its deepest sense. Think about it this way. When we talk about a particle, we describe its properties, its mass, its charge, its spin, its position. These are all pieces of information. When a black hole swallows matter, the information about that matter isn't lost forever. It's encoded perhaps on the black hole's event horizon, in ways we're still trying to fully comprehend. This leads us into the fascinating world of the holographic principle. The holographic principle, a profoundly radical concept, suggests that all the information contained within a volume of space can be entirely described by data encoded on its two-dimensional boundary. It's like our three-dimensional universe is a cosmic hologram, projected from a flat, distant surface. You might be familiar with holograms, those seemingly 3D images that are actually encoded on a 2D film. Well, imagine that on a cosmic scale. This isn't just a fun thought experiment. It arises from attempts to reconcile quantum mechanics with general relativity, particularly in the context of black holes. Stephen Hawking and Jacob Bekenstein's groundbreaking work on black hole entropy suggested that a black hole's entropy, a measure of its information content, is proportional not to its volume, but to the surface area of its event horizon. This was a revolutionary insight. It implies that the information describing everything that falls into a black hole is somehow encoded on its two-dimensional boundary. If this holds true for black holes, could it hold true for the entire universe? If the universe is a hologram, then the quote 101 dawned isn't just a boundary of what we can see or what exists in space-time. It's potentially the very surface where reality's fundamental information is stored. This implies that our perceived three spatial dimensions and even time could be emergent properties, much like the 3D image emerging from a 2D hologram. So if information is fundamental, then the edges we've been discussing, the cosmic horizon, the event horizon of a black hole, take on an even deeper significance. They become not just limits of vision or gravitational pull, but profound boundaries where the very encoding of reality might shift or be revealed. The observable universe, for instance, is an informational edge because it's the limit of the information that has had time to reach us. Beyond that, there's more universe, yes, but the information from it hasn't arrived, and in a rapidly expanding universe, some of it never will. This brings us back to our cosmic horizon, that spherical boundary 46.5 billion light-years distant in every direction. It's a limit to our knowledge, a profound informational edge. We can't see beyond it, we can't receive signals from beyond it, and crucially, we can't send signals beyond it that will ever reach observers there. It's a causally disconnected region from our perspective. The information contained within our observable universe is all the information that has ever been able to interact with us since the Big Bang. But what about the information that does reach us? The cosmic microwave background, CMB for example, is the earliest light we can detect, a snapshot of the universe when it was just 380, 00 years old. It carries an incredible amount of information about the early universe, its temperature fluctuations, its composition, its geometry. It's an informational edge in time, a literal boundary of visibility, beyond which the universe was opaque, a plasma fog where light couldn't travel freely. Now let's pivot from the very nature of reality and information to another kind of ultimate edge, one that lies in our cosmic future. We've talked about the Big Bang as the temporal edge of our universe's beginning. But what about its end? What are the ultimate fates, the final boundaries for this vast, expanding cosmos we inhabit? Our current understanding, driven by observations of dark energy and the accelerating expansion of the universe, points towards a few possible scenarios for the ultimate death or transformation of the cosmos. These are not just theoretical musings, they are predictions based on the laws of physics as we understand them today. The most favoured scenario, given the persistent influence of dark energy, is often called the Big Freeze, or heat death. Imagine the universe continuing to expand relentlessly, forever. As it expands, everything cools down. Galaxies will eventually drift so far apart that they become isolated islands in an ever larger, emptier void. Stars, after billions upon billions of years, will exhaust their fuel and die, collapsing into white dwarfs, neutron stars, or black holes. Even black holes over truly immense timescales are predicted to slowly evaporate through a process called Hawking radiation. Eventually, the universe would become a cold, dark, empty expanse, filled only with a diffuse soup of fundamental particles and photons, all spread so thin that interactions become exceedingly rare. No new stars would ever form. The last stars would have long since faded, and even the most massive black holes would have evaporated into fleeting whispers of radiation. There would be no more energy gradients, no more processes, no more change. It's an ultimate edge of activity, a state of maximum entropy where everything is uniform, cold, and utterly still. It's not an explosion or a collapse, but a slow, quiet fade into oblivion. A universe stretched so thin that it ceases to be anything but a memory of its vibrant past. This is a temporal edge defined by the cessation of all meaningful activity. But what if dark energy isn't constant? What if its influence grows stronger and stronger over time? This leads us to a more dramatic, even terrifying possibility: the Big Rip. In this scenario, the accelerating expansion wouldn't just separate galaxies. It would eventually overcome all gravitational forces, then electromagnetic forces, and finally even the strong and weak nuclear forces. First, galaxies would be torn apart, then star systems, then planets, then atoms themselves. The very fabric of space-time would be ripped asunder, leaving behind only fundamental particles isolated in an ever-expanding, infinitely dilute void. This would be an edge of cosmic destruction, a literal tearing apart of all structure, down to its most fundamental components. Then there's the Big Crunch. A scenario that, while less favoured by current data, remains a fascinating conceptual possibility. If the density of matter and energy in the universe were high enough, or if dark energy's influence were to reverse, the expansion of the universe could eventually halt and then reverse. Gravity would pull everything back together. Galaxies would rush towards each other. Space-time would contract. Temperatures would rise. And eventually all matter and energy would collapse back into an infinitely dense, hot singularity, perhaps similar to the state before the Big Bang. This would be a temporal edge of ultimate collapse, a complete reversal of our universe's history. And if the Big Crunch were to happen, some theories propose a cyclical universe, where the big crunch isn't the final end, but rather a big bounce. A cosmic rebound that initiates a new Big Bang, giving birth to a new universe. Imagine an infinite series of universes, each collapsing and rebirthing like a cosmic breath. In this scenario, the edge isn't a final end, but a transition point, a gateway to the next iteration of existence. These ultimate fates, the big freeze, the big rip, the big crunch, the big bounce, represent the most profound temporal edges imaginable. They are the boundaries of existence itself, the final chapters in the cosmic story. They challenge us to think about timescales that dwarf human comprehension and to confront the impermanence of even the grandest structures in the universe. It's humbling, isn't it, to consider that our entire cosmic history, from the Big Bang to the present, might just be a fleeting moment in the grand scheme of things. These scenarios push the boundaries of our scientific understanding and, frankly, our imagination. They force us to ask not just, quote, 10, but, quote. And in contemplating these vast, ultimate, quote, 12. We also confront an intriguing philosophical edge, the edge of meaning. In a universe potentially destined for heat death or a catastrophic rip, does our existence, our quest for knowledge, our very consciousness, hold any ultimate significance? This isn't a question science can directly answer, but it's a question that science, by revealing the universe's incredible scale and potential fates, inevitably provokes. But rather than despair, I find immense wonder in these questions. It's precisely because the universe is so vast, so mysterious, and its ultimate fate so uncertain, that our journey of discovery becomes even more profound. Our ability to even ask these questions, to formulate theories about information as fundamental or the universe's ultimate end, is a testament to the incredible power of the human mind. We are small, yes, but our capacity for understanding and wonder is immense. We are pushing the boundaries of knowledge, mapping the edges of the known, and peering into the profound mysteries that lie beyond. Each edge we encounter, be it informational, temporal, conceptual, or theoretical, isn't a wall that stops us, but a horizon that invites further exploration. In our next chapter, we'll shift our focus slightly. We've explored the universe's edges, but what about the edge of our perception? How do our senses, our brains, and our very tools shape what we can know about reality? And how are we constantly building new lenses to see beyond these human-imposed limitations? We'll delve into the fascinating interplay between our minds, our technology, and the cosmic truths we seek to uncover. I'm always curious to hear your thoughts on these profound topics. Does the idea of information as fundamental resonate with you? Which cosmic fate seems most compelling or unsettling? Let me know in the comments. For now, let's carry this sense of wonder forward. We've journeyed through the vast, mind-bending possibilities of the universe's ultimate temporal edges, contemplating fates as diverse as the big freeze, the big rip, the big crunch, and the enigmatic big bounce. Each scenario, in its own profound way, represents a kind of cosmic, quote, 116, whether it's the cessation of meaningful activity, the tearing apart of space-time, a collapse into singularity, or the beginning of a new cycle. These are not mere scientific predictions. They are profound philosophical statements about existence itself, aren't they? They force us to ask, If the universe has a beginning and potentially an end, what does that say about its nature? And how do these ultimate temporal boundaries square with the idea of an infinite cosmos? This brings us full circle, back to our central perplexing question. Can the universe be infinite and have an edge? Throughout our exploration, we've discovered that edge is a remarkably fluid concept when applied to the cosmos. It's rarely the solid, impenetrable wall our everyday intuition might conjure. Instead, cosmic edges are more often limits. Limits of information, limits of causality, limits of our current scientific understanding, or even limits of what spacetime itself can do. They are not boundaries within the universe, but often boundaries of our perception or conceptualization of the universe. Think about it. An observable universe with a cosmic horizon isn't a physical barrier. You could theoretically travel past it, only to find your observable universe would simply shift, always centered on you. The edge here is a personal information boundary, a light-speed limited horizon that expands with time. It's a limit to what we can see and know, not a brick wall where the universe stops. Similarly, the Big Bang, our universe's temporal edge, isn't a point in space you could point to and say, quote, "It happened everywhere, simultaneously, marking the beginning of space-time itself." It's a fundamental limit to our ability to extrapolate backward in time using current physics, a temporal edge where our known laws break down. And what about the possibility of an infinite universe? If space truly extends forever without end, how can we talk about any edge? This is where the subtle dance between geometry, topology, and our perception becomes crucial. A spatially infinite universe, by definition, has no physical boundary. You could travel in any direction forever, never encountering a wall. So, if the universe is indeed spatially infinite, then any talk of an edge must refer to something else entirely. This something else is precisely what we've been unraveling. Our Quote 123 are definitions. They define the limits of a given property or phenomenon within the vastness. For instance, the Planck epoch isn't a spatial edge, but a temporal and energetic one, a limit to the conditions under which our current theories of physics hold sway. It's in Quote 124 for our understanding. Black hole singularities are not locations you can simply visit and observe. They are points where the very fabric of space-time is so distorted that our equations yield infinities, marking in Quote 125 and often in Quote 126, from which nothing, not even light, can escape. Consider the holographic principle, a fascinating, highly speculative idea we briefly touched upon. It suggests that all the information contained within a volume of space might be encoded on its boundary. If this were true, it would imply a profound kind of, quote, 127, not a physical wall, but an informational surface that defines the reality within. It turns the concept of a boundary on its head, making the astyantas, to quote 128, not a stopping point, but the source of information for everything inside. It's a bit like imagining our entire universe as a giant, incredibly detailed hologram, where the 3D reality we experience emerges from a 2D surface at its ultimate boundary. How's that for stretching our intuition? But perhaps the most pervasive and humbling, quote 129, we face are the ones residing squarely within our own current understanding. dark matter and dark energy. These aren't just missing pieces of a puzzle. They represent a staggering 95% of the universe's total mass energy content. Think about that for a moment. 95%. We are effectively living on the very edge of our comprehension when it comes to the vast majority of what makes up the cosmos. Dark matter, which we infer through its gravitational effects, forms the invisible scaffolding upon which galaxies are built. Dark energy, even more mysterious, is the unseen force accelerating the universe's expansion. These aren't distant theoretical boundaries at the edge of the universe. They are fundamental components of the universe, present everywhere, yet utterly alien to our current physics. We don't know what they are made of, how they truly behave, or why they exist. They are, in essence, an immense edge of ignorance that defines the frontier of modern cosmology. When we talk about dark matter and dark energy, we're not talking about a spatial edge where the universe suddenly changes its composition. Instead, we're talking about a conceptual edge, a boundary of our knowledge. It's like standing at the edge of a vast unexplored continent. We know it's there, we see its effects, but we haven't yet charted its landscapes or understood its true nature. This, quote 131, isn't a physical barrier. It's an intellectual challenge, an invitation for new theories, new observations, and new breakthroughs. It represents the very limit of our current models of reality. And this is truly exciting, isn't it? Because these edges, whether they are informational horizons, temporal beginnings, conceptual limits, or regions where physics breaks down, are not obstacles that stop us. They are signposts that guide us. They tell us where the next great discoveries lie. They point to the places where our understanding is incomplete, where new physics might be hiding, where our theories need to be refined or even completely overhauled. The universe, in its potential infinity, doesn't present us with a definitive, quote, "Thrustya sign." Instead, it offers a continuous series of intellectual frontiers. Each, quote, 34, we identify as not an end, but a beginning, a launching pad for deeper inquiry. It's a testament to the human spirit of curiosity that we, tiny beings on a pale blue dot, can even formulate such grand questions and devise methods to probe the most profound mysteries of existence. Our brains are wired for patterns, for boundaries, for beginnings and ends. This is how we navigate our terrestrial world. But the universe, in its magnificent strangeness, often defies these intuitive notions. It challenges us to expand our definitions, to embrace ambiguity, and to find order in what initially appears chaotic or contradictory. An infinite universe having an edge is one of those beautiful paradoxes that forces our minds to grow, to see beyond the obvious, and to appreciate the subtle complexities of reality. So, when we ask, can the universe be infinite and have an edge? The answer we've found is a resounding yes, but only if we redefine what quote 137 truly means. It's not a cliff you can fall off or a wall you can bump into. It's the limit of our sight, the beginning of time, the breakdown of our laws, the boundary of our knowledge, or the very definition of space-time's properties. These edges don't diminish the universe's potential infinity. They enrich it, providing structure and meaning to its boundless expanse. They are the contours of cosmic reality, the fascinating places where our current understanding meets the profound unknown. In our journey, we've learned that the universe is not just vast in size, but vast in its conceptual depth. It's a tapestry woven with threads of information, energy, matter, and space-time, stretching beyond our immediate grasp. The edges we've explored are simply the intricate patterns within that tapestry, revealing its complexity and inviting us to look closer, to understand more deeply. The quest to understand these cosmic edges is, in many ways, the quest to understand ourselves, our place in the cosmos, the limits of our perception, and the boundless potential of human inquiry. Each question answered leads to a dozen more. Each solved mystery unveils a new, deeper enigma. This is the enduring allure of science, the never-ending adventure of discovery. The universe doesn't stop at an edge. Our understanding begins its next leap there. And that, my friends, is perhaps the most wondrous discovery of all. What does this journey through cosmic edges stir within your mind? What new questions bubble to the surface when you contemplate these limits and infinitudes? I'm always curious to hear your thoughts, your own edges of understanding, and the new frontiers you envision. So we've journeyed through the cosmos, haven't we? From the Big Bang's fiery dawn to the distant, chilling whispers of a potential big freeze or rip, we've explored the universe's ultimate temporal edges. These aren't just theoretical endpoints, they're profound conceptual boundaries that frame the very existence and evolution of everything we know. But now it's time to bring it all back to that central captivating paradox that ignited our entire exploration. Can the universe be infinite and have an edge? It's a question that, on the surface, seems to defy logic, right? Our everyday intuition screams, quote, 141. If something is infinite, it has no end, no boundary, no limit. An edge implies a stopping point, a demarcation. How can an endless expanse also have a border? This is where the universe, in its magnificent complexity, challenges our earthbound perspectives and expands the very definition of what Antastias, quote 142, can be. Let's unpack this, piece by illuminating piece. First, consider the infinite part. Our current cosmological models, especially those supported by the remarkably uniform and flat geometry revealed by the cosmic microwave background (CMB) radiation, point strongly towards a spatially infinite universe. Imagine a perfectly flat, endless sheet of paper. You can travel across it forever, never encountering a barrier, never reaching a back or a side that stops you. This is the simplest, most natural implication of a flat universe. It just keeps going, forever. There's no, Cestus quote 146 as gods of it, because it encompasses all space. If you could somehow travel in a straight line, you would never return to your starting point, because there is no boundary to loop around. But if this is true, if space itself truly stretches without end, how can we possibly talk about, quote, 147. Here's where the definition shifts, where our journey through the universe's mysteries truly pays off. The Sand, quote, 148. We've been discussing aren't physical walls or fences in space. They are not barriers you could bump into, nor are they a place where the universe stops. Instead, they are profound limits of a different, more nuanced kind. Think back to the observable universe. This is our most immediate and tangible. Quote, 149, isn't it? It's a sphere of approximately 93 billion light-years in diameter, centered on you. Everything within that sphere is information that has had enough time, given the finite speed of light, to reach us since the Big Bang. Anything beyond that sphere, no matter how vast or how close in cosmic terms, remains unseen. It's not that the universe stops there. It's simply that the information from those regions hasn't reached us yet. This is an informational edge, a limit to what we can perceive, a horizon of knowledge, and critically, this edge is constantly expanding as light from more distant regions finally arrives. It's a dynamic, personal boundary, not a universal one. Then we have the old temporal edge, the Big Bang. This isn't an edge in space, but an edge of space-time itself. About 13.8 billion years ago, space-time, energy and matter all began. There was no, quote, 150. The Big Bang in any meaningful sense that our current physics can describe. It's the ultimate start button for our universe. So while space might be infinite now, it had a definite beginning in time. This temporal edge doesn't contradict spatial infinitude, it frames it. An infinite line can still have a starting point if you're only considering its positive direction, right? Our universe, even if spatially infinite, has a finite history, and looking to the future, we explored those potential ultimate fates, the Big Freeze, the Big Rip, the Big Crunch, or the Big Bounce. These are also temporal edges, defining the ultimate end states or transformations of our universe. Whether it's a cold, dark, empty expanse, a universe torn apart at its seams, or one that collapses back into a singularity, these scenarios represent final conceptual boundaries to the universe's evolution. They are, quote 151 to its story, not to its spatial extent. Beyond these, we delved into the edges of our understanding, the singularities at the Big Bang and within black holes, the Planck epoch where our current physics breaks down. These are not physical places but conceptual frontiers. They are the limits of our current theories, places where the known laws of physics cease to apply, beckoning us to develop a more unified and complete picture of reality. They represent an epistemological edge, a boundary of what we currently know and can explain. And let's not forget the vast, shadowy realms of dark matter and dark energy. These make up 95% of the universe's mass energy, yet their true nature remains largely unknown. They are, in a very real sense, the edge of our ignorance, a profound mystery that drives the universe's accelerating expansion and shapes its destiny. We know they exist because of their gravitational effects, but we don't know what they are. This edge isn't a physical barrier, it's a challenge, an invitation to further scientific discovery. Even the speculative ideas of the multiverse suggest, quote, 152, not physical walls but boundaries between different cosmic bubbles, different quantum realities, or even different mathematical structures. These are conceptual, quote, 153, between distinct realities, not within a single, infinite spatial expanse. So when we ask, quote 154, the answer is a resounding yes, but it requires us to shed our intuitive terrestrial understanding of what an quote 155 truly is. The universe can be spatially infinite, stretching endlessly in all directions, while simultaneously possessing an informational edge, the observable universe, that limits what we can perceive. Temporal edges, the Big Bang and potential future fates, that define its beginning and ultimate evolution. Conceptual edges, singularities, Planck epoch, that mark the limits of our current scientific theories. An epistemological edge, dark matter, dark energy, that represents the frontiers of our knowledge, and potentially metaphysical edges, multiverse boundaries between different realities. None of these, or as on quote 156, imply a physical barrier that stops the universe, or where it runs out of space. They are not like the edge of a table or the boundary of a country. Instead, they are profound signposts marking the limits of our perception, our understanding, and the very fabric of space-time's history and future. I find it utterly fascinating how cosmology forces us to confront the limitations of our everyday language and intuition. Our brains evolve to navigate a finite local environment where edge means a physical boundary. But the cosmos operates on scales and principles that stretch the very fabric of our understanding, demanding new definitions and a more expansive way of thinking. The universe, in its vastness, is both infinitely grand and intimately knowable, piece by piece. These edges aren't roadblocks. They are the very places where science thrives, where new questions are born, and where our quest for understanding truly begins. They are the frontiers of discovery, constantly challenging us to refine our models, push the boundaries of technology, and expand our minds to encompass the truly mind-bending nature of reality. The journey to understand these edges is an ongoing one, a testament to humanity's insatiable curiosity, and as we continue to peer deeper into the cosmos, to listen to its ancient whispers, and to unravel its intricate laws, we come to appreciate that the universe is not just a collection of stars and galaxies, but a dynamic, evolving mystery, full of both boundless expanse and profound, meaningful limits. It's an adventure without end, where every, quote 159, we discover only opens up a new vista of wonder, and so we've journeyed through the ultimate cosmic fates, exploring the theoretical destinies that might one day mark the final temporal edge of our universe. From the slow, cold embrace of the Big Freeze to the violent tearing of the Big Rip, the potential for a fiery Big Crunch, or the endless cycle of a Big Bounce, each scenario paints a vivid, if daunting, picture of an ultimate conclusion. These aren't just abstract ideas. They represent the grand finale of a story billions of years in the making, a story in which we are but fleeting characters, yet also its most fervent narrators. But what does this grand tour of edges truly mean for our initial paradox? Can the universe be infinite and have an edge? As we reflect on our journey, the answer we realize is a resounding yes, but only if we allow our understanding of edge to transcend the simplistic, intuitive definition our everyday experience imposes. Our minds, wired for a world of finite spaces and tangible boundaries, instinctively crave a cosmic fence, a place where the universe simply stops. We picture a vast, boundless expanse, and then, abruptly, a brick wall or a shimmering veil beyond which there is nothing, or perhaps something entirely different. This is the edge our intuition screams for, a physical limit to existence itself. But the universe, in its magnificent indifference to our human preconceptions, offers no such comfort. Instead, it presents us with a far more intricate, far more profound tapestry of limits. Limits not of space, but of information, of time, of causality, of understanding. Think back to our informational edge, the cosmic horizon. It's not a wall, but the limit of light's journey to us, a boundary defined by time and the speed of light. It expands as we age, a dynamic, observer-centric sphere that tells us not about the universe ending, but about the universe revealing itself to us over time. Then there's the Big Bang, our quote. 64. Not an explosion in space, but the very genesis of space-time, a moment before which our current physics, and perhaps existence as we know it, simply didn't apply. And what about the strange geometries of space-time, where a truly infinite, boundless universe can still possess a finite curved volume, much like an ant traversing the surface of a sphere, never finding an edge, yet confined to a finite surface? These are the conceptual leaps our brains are asked to make, right? To shed the comforting notion of a hard stop and embrace the idea that an edge can be a horizon, a beginning, a boundary of knowledge, or even a dimension beyond our direct perception. The universe isn't stopping at these edges, it's simply changing its nature, or revealing the limits of our current methods of observation and comprehension. It's an incredibly humbling realization, isn't it? To acknowledge that our most fundamental definitions might need to stretch and contort to encompass the truly alien reality of the cosmos. This exploration has also been a journey into the very heart of human curiosity. Why do we ask these questions? Why do we spend countless hours, billions of dollars, and generations of brilliant minds peering into the abyss, deciphering the cosmic code? It's not just about satisfying an intellectual itch. It's about understanding our place, our origins, and our destiny within this grand, unfolding drama. It's about pushing the boundaries of what it means to know. We are the universe's way of knowing itself, a fascinating thought I'm always drawn to. Our brains, these complex arrangements of atoms forged in the heart of stars, are grappling with the very laws that govern those stars and the space between them. And yet, for all we've uncovered, for all the profound insights we've gained into the nature of these, quote, 165, the universe holds its deepest secrets close, indeed, the most significant. Quote, 166. We face today are not physical boundaries in space, but the frontiers of our own scientific understanding. These are the true edges of our current knowledge, the places where the known dissolves into the unknown, beckoning us forward with the promise of revolutionary discovery. Let's revisit some of these profound epistemological edges, as we called them, the vast unknowns that continue to challenge and inspire us. First, there's the enduring mystery of dark matter and dark energy. Together, they constitute an astonishing 95% of the universe's total mass energy content. Think about that for a moment. 95%. Everything we can see, everything we can touch, everything that makes up our planets, stars, galaxies, and even us, is just a mere 5% of the cosmic pie. The rest is shrouded in an enigmatic veil. Dark matter, we infer its existence through its gravitational pull on visible matter, holding galaxies together, shaping the large-scale structure of the cosmos. But what is it? Is it a new exotic particle that interacts only weakly with our familiar forces? Is it something stranger still, hinting at modifications to gravity itself? We search for it with sophisticated detectors deep underground, hoping to catch a glimpse of its elusive nature, but it remains, for now, a profound conceptual edge. And then there's dark energy, the even more perplexing force driving the accelerating expansion of the universe. It's as if the cosmos isn't just expanding, but actively pushing itself apart, faster and faster, defying the gravitational pull that should be slowing it down. Dark energy is the dominant component of our universe, yet its nature is perhaps the greatest puzzle in modern cosmology. Is it a property of space-time itself? Quote 168, as Einstein once theorized. Is it a dynamic, evolving field, something we call quote 169, that changes over time? Or is it a sign that our understanding of gravity on cosmic scales is fundamentally incomplete? The answers to these questions lie beyond our current quote 170 just of knowledge, representing a vast, unexplored territory that promises to reshape our understanding of physics. Beyond the dark components, another critical quote 171 lies at the very heart of physics itself, the quest for a unified theory of quantum gravity. We've seen how our understanding breaks down at singularities, those points of infinite density within black holes, and at the very beginning of the universe, the Big Bang. At these extremes, the two pillars of modern physics, Einstein's general relativity, which describes gravity and the large-scale structure of the cosmos, and quantum mechanics, which governs the subatomic world, simply refuse to play nicely together. They offer contradictory descriptions, creating a conceptual chasm, and quote 172, where our current scientific tools fail. To truly understand what happened in the first tiny fractions of a second after the Big Bang, or what lies beyond the event horizon of a black hole and into its singularity, we need a theory that reconciles these two giants. Theories like string theory or loop quantum gravity are valiant attempts to bridge this gap, to smooth out the infinities and provide a coherent description of reality at its most fundamental scales. But for now, they remain theoretical frameworks, their predictions largely beyond our current experimental reach. This, quote 173, isn't a physical place. It's a profound intellectual challenge, a testament to the limits of our current theoretical toolkit. And what about the very fabric of space-time itself? We've explored the radical idea that space-time might not be fundamental. This concept stretches the very fabric of our understanding, suggesting that space and time, which we perceive as the unchanging stage upon which all cosmic events unfold, might actually be emergent phenomena. Like the wetness of water, which emerges from the collective behavior of individual H2O molecules, space-time could arise from a deeper, more fundamental reality that we don't yet comprehend. This, quote 174, pushes us to question our most basic assumptions about reality, inviting us to imagine a universe where space and time are not primal elements, but rather sophisticated illusions, born from something even more abstract and profound. If this is true, then our entire exploration of quote 175 within space-time might be missing an even deeper layer of reality. Finally, we return to the grand, speculative, quote 176 of the Boundless multiverse. While we discussed its various levels, from infinite extensions of our universe to bubble universes, quantum branches, and mathematical structures, the ultimate question remains: is there any direct evidence? For now, the multiverse hypotheses exist largely in the realm of theoretical physics and philosophical conjecture. They offer elegant solutions to certain cosmic puzzles, like the fine-tuning of our universe's constants, but they remain at the farthest reaches of our observational capacity. The edge of the multiverse is not just a boundary between realities, it's the boundary of what we can currently confirm, a tantalizing glimpse into what might be, but what we cannot yet prove. These are the true frontiers, my friends. These are the edges that truly define the limits of our current human knowledge, the places where our understanding falters, but where our curiosity ignites. They are not barriers to exploration. They are invitations to innovate, to theorize, to build bigger telescopes and more sensitive detectors, to push the very limits of human ingenuity. So, can the universe be infinite and have an edge? Absolutely. We've seen how edge takes on a multitude of meanings, a horizon of information, a temporal beginning, a topological boundary, a conceptual limit to our physics, an epistemological frontier of ignorance, or a speculative boundary between realities. Each of these edges is not a wall where the universe stops, but rather a point of transition, a limit of perception, or a conceptual challenge that drives us to understand more. This journey has shown us that the universe is far stranger, far more complex, and far more beautiful than our intuitive minds might initially grasp. It constantly challenges us to redefine our terms, to expand our thinking, and to embrace the awe-inspiring reality that surrounds us. The paradox dissolves not by finding a simple answer, but by expanding the very definitions within the question itself. And this perhaps is the greatest lesson. The universe isn't just a collection of stars and galaxies, it's an ongoing conversation, a perpetual invitation to wonder. Our quest to understand its edges is, in essence, a quest to understand ourselves, our capacity for knowledge, our drive for discovery, and our profound connection to the cosmos from which we emerged. As we conclude this chapter of our exploration, I'm left, as always, with a sense of immense wonder and an insatiable desire to know more. The universe continues to unfold its mysteries, one, quote, 180 at a time, and we, the curious inhabitants of this pale blue dot, are privileged to be its witnesses and its interpreters. Thank you for joining me on this incredible journey. Keep those questions coming. Keep that curiosity burning brightly. Because the universe, infinite or not, with its many edges, is always waiting for us to explore. Welcome back, cosmic explorers, to Dreamy Science. Our journey through the universe's most perplexing paradox has been nothing short of mind-bending, hasn't it? We've wrestled with the fundamental question: can the universe be infinite and have an edge? And as we've peeled back the layers of cosmic mystery, our answer has become a resounding, albeit nuanced, yes. You see, the best quote. 81. We've been searching for isn't the simple physical barrier our everyday intuition might conjure up. It's not a brick wall at the end of space, nor a precipice from which the cosmos falls away into nothingness. Instead, we've discovered a breathtaking tapestry of, quote 182, limits not of space itself, but of information, of time, of causality, of our current scientific understanding, and even of our very conceptual frameworks. These aren't stops. They are dynamic, ever-shifting frontiers that invite us to look further, think deeper, and challenge everything we thought we knew about reality. But why is this so difficult for our brains to truly grasp? Why does the idea of an infinite universe with these ephemeral conceptual edges feel so counterintuitive? It's because our minds are magnificent, yet fundamentally limited by our evolutionary experience. We are creatures of the terrestrial, wired to navigate a finite three-dimensional world where boundaries are typically solid and observable. Our brains excel at understanding objects, distances, and durations that are relatable to our human scale. We see a wall, we know it's an edge. We see a horizon, we understand it as a limit to our vision. When we stretch these familiar concepts to the cosmic scale, to distances of billions of light years, to durations of billions of years, to the very fabric of space-time itself, our intuitive frameworks begin to buckle. How do you visualize an infinite, spatially flat universe? How do you mentally encapsulate a point in time, the Big Bang, that was everywhere at once? Not in space, but the beginning of space. It's like trying to describe the color blue to someone who has only ever seen in black and white. The conceptual leap requires a complete recalibration of our mental apparatus. Our human intuition, while incredibly useful for survival on Earth, often finds itself utterly overwhelmed when confronted with the universe's true vastness and its strange, beautiful geometries. This is precisely where science steps in, offering us a language and a methodology to transcend our innate limitations. Mathematics, in particular, becomes our most powerful lens, allowing us to describe realities that our senses cannot perceive and our imaginations struggle to picture. Through equations and models, we can explore dimensions beyond our three spatial ones, conceptualize infinities that don't fit into any physical container, and chart the evolution of space-time from a singularity to the expansive cosmos we inhabit today. Science doesn't just observe, it constructs frameworks that push the very boundaries of human thought, expanding our intuition rather than being constrained by it. And it's at these very edges that the most exciting scientific breakthroughs are waiting to happen. Consider the epistemological edge, the vast uncharted territory of dark matter and dark energy. This isn't a theoretical limit. It's a profound observational mystery that represents a staggering 95% of the universe's total mass energy content. We know they are there because we see their gravitational effects, dark matter shaping galaxies, dark energy accelerating cosmic expansion, but we don't know what they are. This edge isn't a barrier, it's an enormous luminous question mark, driving thousands of scientists worldwide to devise new experiments, build more sensitive detectors, and formulate revolutionary theories. Imagine the paradigm shift, the complete rewriting of our cosmic story, when we finally unravel the true nature of these enigmatic components. That's an edge that promises not an end, but an entirely new beginning for our understanding. Then there's the conceptual edge, the realm where our current physics breaks down. Think about the singularities at the heart of black holes or the universe's initial moments during the Planck epoch. Here, our two most successful theories, general relativity, describing the very large, and quantum mechanics, describing the very small, become incompatible. This is an edge of predictability, a boundary beyond which our current scientific tools simply cannot venture. But rather than a frustrating dead end, it's a powerful motivator. It tells us that our understanding is incomplete, that there's a deeper, more fundamental theory waiting to be discovered, a unified theory of quantum gravity. Imagine what new insights into the nature of space-time, energy, and matter will emerge when we finally bridge this monumental gap. This edge beckons us to forge new conceptual tools, to envision a reality more profound than our current models allow. And let's not forget the tantalizing, though highly speculative, metaphysical speculative edges of the multiverse hypothesis. While lacking direct observational evidence, yet these ideas push the very definition of what we mean by. Quote 184. Are there other bubble universes born from eternal inflation? Are there infinite repetitions of our own cosmic history? These aren't just abstract philosophical musings, they are testable, in principle, hypotheses, forcing us to consider the possibility that our universe is but one leaf on an unimaginably vast cosmic tree. The edge here isn't a wall, but a conceptual expansion, urging us to question the uniqueness of our existence and the ultimate limits of physical reality itself. It's an invitation to dream bigger, to imagine beyond the confines of our known cosmos. What's truly remarkable is the dynamic nature of these edges. They are not static, fixed boundaries. Our observable universe, as for instance, is constantly expanding as light from ever more distant galaxies finally reaches us. The TMD quote 185 of our information horizon is perpetually receding, offering new vistas into the past and present of the cosmos. Similarly, the quote 186 of our knowledge, dark matter, quantum gravity, are not insurmountable walls. They are active research frontiers, constantly being probed, chipped away at, and potentially moved or even dissolved as new discoveries emerge. The universe, in its infinite complexity, is always revealing new layers, new challenges, and new wonders. This entire exploration, from the Big Bang to the potential multiverse, ultimately brings us back to a profound realization. The universe is far more intricate, more counterintuitive, and more awe-inspiring than our everyday experience could ever suggest. It challenges us to expand our minds, to embrace the unknown, and to find beauty in the very limits of our understanding. These, quote 187, aren't limitations of the universe itself, but rather markers of our current position on a never-ending journey of discovery. They define the boundaries of what we currently know, yes, but more importantly, they illuminate the vast, exciting expanse of what we can still learn. So when you next gaze up at the night sky, remember that you are not just looking at stars and galaxies. You're looking at an infinite canvas dotted with countless edges, edges of light, edges of time, edges of knowledge, and edges of pure speculation. Each one is an invitation, a cosmic whisper urging you to ponder, to question, and to join in the grand adventure of unraveling the universe's deepest secrets. It's a journey without a final destination, a quest that continuously redefines our place in the cosmos. And that, my friends, is why science is the most exhilarating exploration of all. I'd love to hear your thoughts on these various edges. Which one fascinates you the most? Which one do you think will conquer first? Share your insights in the comments below, and join us next time as we dive even deeper into the mind-bending implications of cosmic scales and the ongoing quest to understand them. Until then, keep looking up, keep wondering, and keep exploring,